Hello again, everyone. We are going to continue the discussion. This is still the first lecture. As I said, I have just decided to separate this lecture so you can always have access to the other one pretty easily. And this is going to be the official start of the science of propulsion, essentially. This is, again, is going to be a short lecture because your first chapter is pretty short and very light on mathematics. So essentially, we want to have a historical perspective to propulsion. As you, most of you guys should know about this because it's a very famous event. Powered flight started with the Wright brothers in North Carolina, pretty close to us, in 1903. They actually used the reciprocating combustion engine, which only had 12 horsepower. So up until this point, this is an internal combustion engine with cylinders, propellers, and everything. The propulsion devices are not in yet. But then in the 1930s, a guy called Frank Fiddle, who was a British guy, who was a British person, patented the gas turbine, the idea of the gas turbine essentially, with the Brighton cycle and everything. And the gas turbine is designed based on the Brighton cycle compared to the Rankine cycle. And my expectation and understanding is that you guys are already familiar with all of these cycles, like Brighton cycles, Rankine cycle, and all of it. But if you are not, and if they haven't covered it for you in your thermodynamics course, that is all right. You just have to let me know. Okay, but we will do a very small review of the Brighton cycle, and we will solve some example that relates to the Carnot cycle, which is the ideal thermodynamic cycle, and the Brighton cycle itself. And we will introduce a new cycle called the Humphreys cycle, for which you have to solve. You will definitely solve a homework problem or a quiz problem. Okay, so what is the Brighton cycle? It's very simple. You have a Brighton cycle is comprised from a compressor that is connected to a turbine through a shaft. Okay, and the shaft is rotating, and this is how you get your work out. Okay, you have air coming in. That's the first point of the cycle. Air, fresh air, and then the air is compressed in the compressor, goes to combustor, to which the fuel is added as well, and you will have combustion. I'm sorry. And then this, to the third part of the cycle, goes to turbines to move the turbine blades and help the combustion process, help the compression process as well. And then point 4 of the cycle, you will have your exhaust gas going out. Okay, so this is a very simple overview of the Brighton cycle. Compared to a Rankine cycle, if you recall, Rankine cycle was a closed cycle. So whatever happened, whatever was included in the Rankine cycle stayed there. You had a boiler, you had all of those things, but we don't deal with the Rankine cycle. If you ever take a power plant design course, that's all they're talking about. But in a propulsion course, we are interested in gas turbines and the Brighton cycles or a modification of this specific type of cycle. So it's an open system cycle, essentially. Okay, so the patent created the gas turbine. The patent filed in Britain by this guy, Frank Fiddle. was about the gas. It was the first patent about the gas turbine, essentially. That started the propulsion age. Okay, let's talk about the Brayton cycle a little more. You know from your thermodynamics that PV diagrams and TS diagrams are very important in cycle analysis. So for a Brayton cycle, that's what you see. This is going to be your Brayton. We have another cycle here, which we will discuss here. Let me actually draw this on the other page. Okay, so your TS diagram will be something like this: 1, 2, 3, 4. Okay, and these are a combination of two different cycles. That's why we don't have that's why the numbers are different. Okay, you have constant pressure happening here from 1 to 2. You have constant pressure happening here from this is a TS diagram. Yeah, constant pressure happening here in the turbine, and then you have constant entropy happening from 2 to 3 and 4 to 1. And I mean, as you should definitely note that these are all ideal cycles. So in the real world, we are adding fuel from 2 to 3. There's combustion happening, but the assumption is that the air is so compressed that when you move it to combustion, it starts exploding essentially with a constant entropy in a constant entropy process. And the PV diagram, as you can see, we still have this is going to be your Brayton cycle. Constant pressures and constant entropy. Okay, and we can do a lot of calculations. If we end up having these TS diagrams, we can do the thermal efficiency calculations and all, which we'll discuss later in this lecture. Okay, let's go back to the history. So the first gas turbine that was actually built was built by a German guy, and his name is Hans Joachim Pabst von Ohain. I'm pretty sure my pronunciation is way off, but he invented the turbojet engine. He was the first one. They did it in parallel. They weren't talking to each other. The German ones was unfortunately geared toward the war effort, German World War II war effort. But yeah, and he granted the patent in 1936. It was the first one that was built, the turbojet. It produced a thrust of 250 pounds and at 1,000 RPMs. And he was one of the inventors of the air-breathing gas turbine engine as well. As this, the first gas turbine that was built was set up on this aircraft, which is Messerschmitt ME262. I'm not pretty sure about the pronunciation again, which had two of the Jumbo 004B turbojet engines. That was the first turbojet engine that was ever manufactured, ever built. Okay, and this is a schematic of that specific engine. As you can see the compressor parts, you can see the combustion and the turbine part, and you can see all of those parts. You can see the inlet, the outlet. And one cool thing they did was that they had this air build mechanism that essentially bleeded air from the combustor to the turbine for the blade cooling. And this is a very important process because cooling in general is very important. It's a very important part of your propulsion mechanism. You have some explosion happening, you should be able to cool your turbine blades to make sure that they will operate at 100% efficiency and they will operate for a long time. Okay. So just a very brief historical perspective. We are not going to go into too much detail. We will have some flashback to the history during the course of the semester, and we will have some discussions about what's going to happen in future with the combustion systems. But I have some innovations, if you will, in the aircraft, newer innovations in the aircraft gas turbine engines. Most of this innovation has happened during the past 30 years or are work in progress. So that hasn't happened yet, essentially. The idea is that we want to have high pressure compression systems. We want to increase the pressure ratio. We will talk about all of these things later on. This is an introduction lecture, so just bear with me if you are confused or unclear about these things. You can always go and read more yourself, and yeah, we can talk. We have the multi-spool configurations, which you can see here. We can see the multi-spools here. That was developed by Pratt and Whitney. We can have the variable stator. That was developed by GE. And we can also have the transonic compressors, because this transonic compressor is actually a very important part of these innovations, because compression at supersonic and transonic speed is always a huge problem. In the supersonic speed, you usually use ramjets and scramjets, so we don't really do the compression, classic compression, if you will, gas turbine compression. But in the transonic region, we still need some sort of a compressor, and we need to be able to come up with a way to do this compression. So this is a very important uh, part of transonic flights, supersonic flights. Okay, the other innovations happen in the combustors, like the environmentally friendly, low emission combustors, or more efficient combustors in general. Turbine cooling, as I mentioned, is a very important part of the process. You want to keep your turbine healthy, essentially. You want it to run as much as possible. And playing with the exhaust nozzles, that started from World War II again. Most of these things, most of the propulsion age started from World War II. So that's something to keep in mind. The exhaust nozzles, playing with with their direction, with the circumference of the exhaust nozzle, the outlet there, is always a very interesting thing and results in very interesting phenomenon as well. As you can see, the exhaust nozzle here is geared toward the beneath the aircraft, toward the earth, essentially, instead of just exhausting air to the back. This will definitely affect your thrust, right? And it will give you a lot of other controls, like the thrust vectoring. All of these are controlling the direction of the thrust. And also, another important part of the innovations in gas turbine design is better manufacturing, like using composites or better manufacturing in general, which is mostly geared toward more durable devices and lighter devices specifically. So you will need less energy. This is an example of the F-22 thrust vectoring mechanism that changes the direction of exhaust. As you can see, it goes from negative 20-degree thrust vector to a positive 20-degree thrust vector. Thrust vectoring is something that you will hear about in your aircraft design. We'll hear more about in aircraft design. We will talk a little bit about it here. What are the applications of thrust vectoring? But essentially, it means that your exhaust gas angle is changing. Okay, and some examples of the new concepts of manufacturing: lighter compressors, the compressor weight reductions, using composites, and all of those things. Hopefully, at this point, you have already passed your manufacturing class. You have a good idea of what composites are and what they are used for. And they're pretty important in propulsion design parts, which is not the focus of this course. We are mostly focused on the fluid mechanic parts of the propulsion. Okay, there are general new engine concepts that's gonna further the idea of gas turbines and jet engines. Like we have the advanced turboprops and gear turbofans that was developed by NASA, and there are advanced air breathing rocket technology and wave roller topping cycles. Also, a lot of things that are happening in the cooling of the systems that are very interesting, and we will discuss this in more detail later on in the chapter. Okay, so let's go back to the Humphrey cycle, which is a newer cycle that is used in the newer engines in the innovations. It's called the Humphrey cycle versus the Brayton. The difference between the Humphrey cycle and the Brayton cycle goes back to this TS diagram. Okay, so what happens here inside your combustor, I think I went the wrong way in that design analysis. Sorry about that. That was my mistake. Unbelievable mistake. So we go from here to here to here for the Brayton cycle. So your Brayton cycle is 1, 2, 5, 6, 1. Okay, this is your Brayton cycle. Constant pressure happening inside your combustor, and constant pressure from exhaust to inlet. So this part of the cycle is not really there because you are exhausting in air. So air is not coming back, but for the design analysis, we usually assume that there is a cycle going on. And this is the feature of open cycles, that your exhaust doesn't go back to the inlet. Okay, so yeah, I'm sorry about that mistake. Just make sure that you are clear. We go from 1 to 2 to 5 to 6 for the Brayton cycles. Pressure constant at the combustor, pressure constant at the exhaust to inlet, and then we have the entropy constant at the turbine and compressor. Okay. What's the difference inside the combustor is that, as you can see here, there are some differences in design. Okay, this is a more complicated system. We have 2 turbines, we have a couple of compressors, we have a fan. So this cycle analysis is gonna be different. But the simplest one for a Humphrey cycle is gonna give you is gonna go from 1 to 2 to 3 to 4 to 1. Okay, and here inside the combustor, we're gonna have a constant volume process happening. The mechanism behind it we'll get to later on, but this is the main difference. And of course, the PV diagram is going to be different as well. 1 to 2. So instead of having a constant pressure, we have a constant volume. Okay. And then 2, 3 to 4. Okay. So it definitely is going to affect your thermal analysis. This time you have to include the temperature at different points. T3, you have to include the temperature after the combustor as well. But in the regular cycles efficiency analysis, you don't need to include the temperature after the combustor. Yeah, so for the Brayton cycle, the efficiency is 1 minus T1 over T2, the ratio of T1 over T2. And for the Humphrey cycle, you will have this huge ratio, and proving this ratio is going to be part of a quiz or a homework for you guys. Okay, and you can see the thermal efficiencies here, the differences in thermal efficiencies. You can see the thermal efficiency of the Humphrey cycle is higher. It goes down as you increase the combustor exit temperature, but it is still at like 2500 Kelvin. It is still higher than the regular Brayton's cycle. Again, going back to the new engine concepts, we have the pulse detonation engines, or PDEs. Essentially, these are very interesting concepts. These are very interesting engines when you have your thrust is going to be complemented, or is going to be there because of this detonation, the small explosions that are happening pulsely, like a lot of frames per second, like 60 detonations per second are happening inside your combustor, at your exhaust, or different parts of it. And these are pretty interesting engines. And another new engine concepts is the millimeter scale gas turbines that are that is a triumph of MEMS and digital fabrication. Essentially, we are going to have we have this design because of the digital fabrication and MEMS. And we also have the combined cycle propulsion that are the newest part of the thing, but it has been on engineers' mind from the get-go that they want to design engines that can take care of takeoff to going to the outer space. Okay, you can see the millimeter scale designs here and the concepts for the combined engines, essentially from takeoff to the return. But the newest frontiers are the UAVs, or uninhibited aerial vehicles. As you can see, NASA has designed a lot of them. And the reason we can do a lot of this analysis is because computational fluid dynamics has advanced a lot throughout the years. So it is right now it is possible for us to test a supersonic, not just the computational fluid dynamics, also non-destructive testing. It is possible for us to test a real designed engine without tearing it apart, okay? Or even test it before even manufacturing through CFD. So these are the things that are pretty important for us and pretty new. These are the new frontiers. That's it for the chapter. That very short chapter, just an introduction to the different concepts. The only thing that you really need to get away as far as solving problems goes, is the cycle analysis. And by that I mean like understanding the TS diagram, PV diagram, being able to calculate the thermal efficiency of a system. I'm going to solve two examples for you here. That is problem 1 of your book. And the problem 1 talks about a Carnot cycle. And as you know, a Carnot cycle is the most ideal cycle that you can have. I will give you the highest efficiency, essentially. And we want to prove that efficiency of a Carnot cycle can be calculated using this if your TS diagram of the system is something like this. This is point A, point 2, point 3, point 4. And we don't know what are the energy levels here, what are the entropy levels here. Just an approximate. We just have the temperatures and pressures at each point. Okay. So how can we prove this? It's very simple. You have to go back to the first law of thermodynamics. Based on the first law, there's no changes in the internal energy because we go back to point 1, right? So I'm sorry. You can calculate the work done by the system or done on the system. In this case, done by the system is the integral of the Q input, essentially the combination of Q input and Q output. Okay. Assumption here for a Carnot cycle is that we are dealing with a reversible heat engine. Please let me know if you don't know what are these concepts, like what a heat engine is. If you don't remember them, that's all right. You can go back and review it. But you have to know this. You have to at least heard about the concept. Okay. And if you recall, heat engine has a hot temperature reservoir and a low temperature reservoir. So the integral of heat input and output is essentially can be calculated by the integral of temperature with respect to changes in entropy, which essentially means that TH minus TL multiplied by delta S. Okay. Let's go to the next page. And your work, so therefore your work is going to be TH minus TL delta S, and Q in is going to happen from 2 to 3. That's your combustor phase for the Brayton cycle. Okay, that's the integral of TdS from 2 to 3, which is essentially TH delta S. Okay, so and we already know that the definition of efficiency in a cycle is work divided by Q in for a heat engine. Okay, just plug in the formulas. TH minus TL delta S over TH delta S. Delta S will go away, and you will get 1 minus TL over TH, which is essentially based on the diagram we have is going to be equal to T1, 1 minus T1 over T2. Okay. And we also, problem 1 has also asked us to calculate the thermal efficiency in case T1 is 288 Kelvin and T2 is 2000 Kelvin. Pretty simple, just plug in the formula. Your efficiency is going to be 85.6%. Okay. So I don't think we have time for another example. By the next example, what we wanted to do was to talk about the ideal Brayton cycle and calculate that the cycle efficiency in a Brayton cycle it should be calculated the same way with the same equation. Of course, the temperatures are going to be different, are not going to be T low and TH anymore, but it's still T1 and T2. That's actually, let's do this for a bonus point. This is something I forgot to mention. Those of you who have already have had class with me know that I give out a lot of bonus points. So let's do this for a bonus point. You have until Monday before the class to submit your bonus points. Or you can just bring it to the class. Okay. I want you to prove that the efficiency of the Brayton cycle is calculated using this formula. There's nothing special to it. Just don't stress out about it. And something that you have to keep in mind is that the efficiency of a thermal cycle also can be calculated by 1 minus Q out over Q in, right? Which in this case is 1 minus Q 421 and Q 223, right? Based on the Brayton cycles TS diagram. Okay, 1, 2, 3, 4. Okay. So this is your bonus points. Just submit it by Monday and you will get 0.5% if you get it correct of your total grade. Okay. I guess that's it for today. We already are over time. And I'm going to see all of you Monday. Stay safe.